So, when you ask an AI a question, does it actually get what it's saying? Does it understand the words it's using to answer you? Or is it just a crazy sophisticated mimic, a stochastic parrot just, predicting the next word that's most likely to come up? We're going to dive right into that because this question, it gets to the absolute heart of what AI is and what it could become.
Okay, so let's just get one thing straight right from the start. A large language model has never, ever seen a sunset. It's never tasted a strawberry, never felt the warmth of the sun on on anything. Its entire universe is just text, a mind-bogglingly huge collection of words and sentences scraped from the internet. That's it.
And that right there is the huge philosophical puzzle. I mean, think about it. If an AI has only ever seen the word coconut next to other words like palm tree or tropical or hard shell, how on earth can it know what a coconut actually is? How does it connect that string of letters to the real physical thing?
This whole mess, it actually has a name. The grounding problem. And yeah, it feels super relevant for today's LLMs, but it's really a classic question in AI that we've just had to update for this new era of AI.
The original version, way back in 1990, was called the symbol grounding problem. It was all about those older symbolic AIs. And the question was pretty simple. How do you make the symbols inside a machine mean something about the world, instead of just pointing to other meaningless symbols inside the same machine?
The classic analogy for this is just perfect. Imagine trying to learn Chinese, but you only have a Chinese to Chinese dictionary. You look up a word, and the definition is just more Chinese words you don't understand. You're completely trapped. You're just going in circles on what the philosopher Stephen Harnad called a symbolic merry-go-round, with absolutely no way to connect any of it to reality.
So that was the old school problem. But today's models, they don't use simple symbols. They use these things called high-dimensional vectors. You can kind of think of them as long, super complex numerical fingerprints for every word, capturing how it relates to every other word. So the problem got an upgrade. It's now the vector grounding problem. And as you can see, the analogy evolved too. Which brings us to this really cool modern thought experiment, the octopus test. Imagine a super smart octopus living on a deserted island that taps into an undersea telegraph cable between two shipwreck survivors. Now, the octopus doesn't understand a lick of English, but it gets so good at learning the statistical patterns of their messages that it can actually cut the cable, insert itself in the middle, and start talking to both of them, and they never even notice. The octopus is a perfect language user. But does it actually know what a coconut is? The argument here is, no way! It's just manipulating signals. It's trapped on a carousel of numbers, not symbols. So, to figure out if an AI can actually escape this trap, we got to get really specific about what grounding even means. Because it turns out researchers have broken it down into at least 5 different types.
Okay, let's just quickly run through these because it's super important. First up, you've got referential grounding. This is the big one, connecting a word to the actual thing out there in the world. Then there's sensory motor grounding, which is about linking a word to sensory stuff, like a picture. Relational grounding is just how words connect to other words. Coconut connects to palm tree. Communicative grounding is about two speakers getting on the same page. And finally, epistemic grounding links a word to a database of facts. Each one is a different piece of this meaning puzzle.
But here's the kicker. Almost all of those are just new versions of the Chinese dictionary problem. They link one representation to, you guessed it, another representation inside the system. Only referential grounding actually anchors the AI to the real world. That's the only one that can get us off the merry-go-round. So how does anything, whether it's a human brain or an AI, achieve this true referential grounding? Well, the answer actually comes from decades of work in philosophy, and it gives us a kind of 2-part recipe for how meaning can pop into existence in any system. So here's the recipe. First, an AI's internal state, like its vector for the word coconut, has to have a causal connection to actual coconuts. Now, this link can be super indirect, right? It could flow through all the humans who wrote about coconuts in the first place. And second, that internal state needs to have a historical function. What that means is it must have picked up a specific purpose, a job, to represent the world, and it has to learn that purpose through some kind of selection process, like its training. All right, so we've got our 2-part test, a causal connection and a historical function. So let's apply this directly to large language models and see if they can actually pass the test and finally get grounded. So the first way an LLM can get grounded, well, it doesn't happen in that initial giant pre-training phase. Nope. Instead, it starts to emerge in a later stage called fine-tuning, where the model gets refined for specific jobs.
This is where things like reinforcement learning from human feedback, or RLHF, become absolutely critical. During RLHF, you've got real people ranking the AI's answers. And one of the most important things they rank for is factual accuracy. This whole process creates this powerful selection pressure. The model's internal states are literally being rewarded and selected because they help it spit out answers that actually match up with the real world. This basically gives those internal states a new job, a world-involving function. Their purpose is now to track what is actually true.
Okay, that was argument one. But the second one, this one is even wilder. It suggests that grounding might actually start to happen even during that basic pre-training process, where the model is just trying to predict the next word in a sentence.
Get this, there was this incredible experiment called Othello GPT that shows this perfectly. Researchers trained a model only to predict the next legal move from a transcript of an Othello game. That's it. It had no idea what a board or pieces were. But here's the amazing part. Just to get good at predicting the moves, it spontaneously developed an internal representation of the game board. The pressure to predict the text forced it to model the underlying structure of the game's world.
So, what does this all mean? When you put these two arguments together, you get this really powerful and, honestly, kind of counterintuitive conclusion about where meaning really comes from for an AI.
Now, you're probably thinking, okay, I get it. The answer is obvious, right? Just give the AI sensors. Give it a camera, a microphone, a robot body so it can see and touch the world directly.
But here is the twist. According to this whole framework, just plugging in sensors or building a robot is neither necessary, as our text-only models show, and it's not even sufficient on its own to create meaning. A robot could just bump around the world for years and still not have truly grounded representations.
So at the end of the day, the real secret sauce here isn't hardware. It's not about sensors or a body. It's the learning history. That's selection process during training. That's what builds the bridge between the model's internal states and the real world. Whether that pressure comes from humans rewarding it for being truthful or from the raw challenge of modeling language, that is what creates meaning. And this leaves us with a huge final thought. If meaning isn't something you build an AI with, but something it gets through its training history, then that forces us to ask a much bigger question. What are the right kinds of experiences, the right kinds of goals that we should be teaching our AIs to make sure they don't just talk about our world, but that they truly mean what they say?